teach that shows up, if you agree to it. Yeah. Okay, I'd like to welcome everybody. I know it's a very busy time for the department with the graduate student symposium, all types of things going on, different seminars. But we're very fortunate today to have Professor Jose Rodriguez-Martinez from Spain visiting us. He's on the way to the Metal Society conference in Orlando, so he graciously agreed to stop by. Professor Martinez is a professor in the Department of Continuum Mechanics and Structural Analysis at the University of Carlos III in Madrid. He also heads up a research group on nonlinear solid mechanics. He holds 2 PhDs, one from the University of Carlos III and one from Mechanics of Materials from the University Paul Verlaine of Metz in France. His research is mostly focused, as we're going to see today, on experimental methods for fracture and flow. He's very active with the European Research Council, a number of grants that fund his activities on that. And he's an associate editor on several journals. One of them is Journal of Engineering Materials and Technology, ASME journal, where I used to be the editor. And he's also an associate editor on International Journal of Plasticity. He's a member of a number of advisory boards, International Council of Theoretical and Applied Mechanics and Euromech and so on. So again, Jose, we're very happy to have you visit us and looking forward to your seminar.
Thank you. Thank you very much for the invitation, Mohammed. It's a pleasure for me to be here. I'm really enjoying this couple of days visiting you and the Department of Material Science and Mechanical Engineering. And thank you, everyone, for coming to the seminar. So the title of the seminar is Dynamic Plastic Localization and Fragmentation of Porous Printed Metals. And I have prepared slides to show you the experiments that we've been performing during the following years. And also the second part of the talk will be multiscale modeling. I don't know if I will have time about talking about the modeling, because I have the feeling that the people is interested in experiments. So I will focus on this, and then we'll see as I'll be showing you the slides. So so the acknowledgement to the European Research Council, which is funding a good portion of this research, but also to the European Union, Marie Curie, different Marie Curie initiatives, to the Ministry of Spain of Science and Innovation, and also to the private foundation of the Bank BBVA or the Air Force Research Laboratory here in the US. So, well, just to give the credit to part of my group, okay, so this is a number of people that they have been involved in most of the results that I will be showing today. So the summary of the talk is, first of all, I'll give an introduction, just a context of the research, okay, let's say the goal and what is the motivation for the research that we have been performing over the following years. Then the objective and the methodology that we've been following. Then, since the main idea is to understand the effect of porosity on plastic flow localization and dynamic fracture, I'll tell you a little bit more about the porosity characterization that we have been performing at the Institute of India Materials using X-ray tomography and different other techniques. And then I will mostly focus on this point 4, showing you the impact experiments that we have been performing, not only in my lab, but also at the European synchrotron radiation facility in France, in Grenoble. Then, as I mentioned, if I have time, I'll show you a little bit about the multiscale modeling, in which basically we are importing the microstructures of the materials into the Abacus finite element code, and then running calculations with the actual microstructure of the materials that we are testing, and then, of course, conclusions and future work. So let's start by the introduction and the research motivation. So when we are talking about impact, I'm basically working on impact mechanics. We are talking about trying to understand the dynamic fracture of materials And a very obvious application is try to improve the energy absorption capacity of different protective structures. This is a endless topic that has attracted the attention of many researchers, not only in Europe, but in fact mostly in the US over the last century, I would say. So, but it's not only about these applications that you may be related to defense or military applications and so on. But dynamic fracture of materials and fragmentation is also very important within the framework of metal forming operations, like high strain rate metal forming operations. I'm just putting here a couple of simple examples that I took from the internet. So for instance, explosive forming operations, basically we have a metal sheet and it is formed at very high strain rates. And the issue here is try to understand what is the formability limit of this specific material. This is an interesting forming process, especially for those materials with low formability, because at very high strain rates, what we find is that because of the viscosity of the material and inertial forces, we can increase the ductility of the metal sheet. And similar here in this another simple example that again I took from internet, just to show you another case in which explosive forming, it is used typically in aerospace industry or for building aircraft parts and so on, in order to be able to obtain extended formability of certain lightweight materials. So this is a little bit like the practical application of the research that we are performing, but certainly we are very much focused on the fundamental part of the problem, and we want to understand how is the interaction between the porosity of, in this case, printed metals, the formation of plastic instabilities, and the ultimate dynamic fracture of the specimen that we are testing. We have to understand that when we are talking about ductile materials, what happens is that before fracture, before fragmentation, we observe the formation of plastic instability. So the material deforms, we have homogeneous plastic flow. At some point, at large strains, because of the adiabatic heating, because of the high strain rates, we see the formation of either shear bands or necks or voids that they grow, develop, and then eventually trigger the dynamic fracture of the material, right? So our idea is to understand, again, the effect of porosity with the excuse of investigating printed porous metals. So we want to understand the effect of porosity on the formation of shear bands, on the formation of necks, on the formation of dynamic voids, and how these plastic instabilities, they affect the dynamic fracture of the specimen. So let's start by necks. How typically we study the formation of dynamic necks at the, in a laboratory environment. So I'm showing here one of the classical experiments. In this case, I took these pictures from a beautiful paper of Rabi, published in 2006 in International Journal of Fracture, where he was using electromagnetic loading in order to expand a ring at very high strain rates. So basically, what I'm showing in these two pictures are two different experiments. Okay, and this thin black line, it is the sample at T1, and this one here is the sample at T2, so larger time. This is T3, T4, T5, and so on and so on. So what we observe is that this ring is being expanded, as I mentioned, at high velocity, and at some point we observe the nucleation of multiple necks, and some of these necks, they develop into fractures, eventually leading to the fragmentation of the experiment. So this is one case, and this is another experiment. And this is a very classical test because what we have is that the specimen is subjected to uniaxial loading. So basically, the ring is pretty thin, right? And if we neglect the effect of the curvature, because the ring is pretty thin, for all purposes, what we obtain is uniaxial tension along the circumferential direction of the sample. Because of the symmetry of the problem, instead of having a single neck, we have several necks which are formed more or less at the same time, and some of these necks, they grow and they induce the final fragmentation of the specimen. So another example, in this case, instead of using rings, using thin wall tubes, It is this experiment that I took from the PhD thesis of Mathieu Xavier from the Commissariat à l'Énergie Atomique in France, where instead of having a 1D problem, we have a 2D problem. So this is not a ring, it is a thin wall tube. The tube is subjected to internal explosive loading. So you can see here how right after the explosion, the tube starts to expand, right? And then eventually we have the formation of multiple, in this case, instead of necks, necking bands. So one after the other. And these necking bands that you can see here very clearly, right? They are aligned with the axial direction of the tube because this is quite long and therefore it is plane strain. And we all, people working on metal forming, know very well that the plane strain direction is the preferential direction for the next to form. So this is another example of how to study dynamic necking and fragmentation in a laboratory environment. So the second type of plastic instability we are interested of, it is shear banding, dynamic shear banding. So again, I will show you some examples about how to study dynamic shear banding at the lab in a laboratory environment. And I will start by these classical experiments, beautiful experiments performed by Marchand and Duffy in the late 80s, early 90s in a series of papers where they were using split Hopkinson torsion bar in order to twist thin wall tubes at the strain rates of the order of 10 to the 3. 10 to the 3, 1500, something like that. So using the torsion bar, basically they were able to take the sample and twist it. You can see these lines here, okay? They were drawn in the surface of the specimen before testing. So before the experiments, these lines were horizontal. This is getting twisted, therefore these lines start to get inclined, tilted like this. And then when we have localization, instead of being a straight line, what we observe is this nonlinearity, which is showing that eventually we're going to have here a shear band and then the final fracture of the specimen. Because this experiment is performed at relatively high strain rates, what we observe is that the adiabatic heating, it is playing a role on the formation of the shear. Another experimental configuration to study shear bands at high strain rates, it is instead of using split Hopkinson torsion bar, like in previous case, it is using a split Hopkinson pressure bar, so the, let's say, usual one. And instead of using a thin wall tube subjected to torsion, we are going to use a very simple configuration, which is a cylindrical specimen with a slot here, right? So this is the so-called Riddle specimen, the shear compression specimen. Basically, we are compressing the sample at high strain rates, again, of the order of 10 to the 3, sigma minus 1, and then we are inducing localized shear deformation just right here, and eventually the formation of a shear band. And another experimental configuration to study shear bands, in this case a little bit higher strain rates, it is the radial collapse of thick wall tubes. This experimental technique was originally developed by Nesterenko in University of California, San Diego. So basically, what we have is a thick wall tube. This is just the cross-section of the tube, okay? Cross-section. So it's a thick wall tube which is subjected to compression, radial compression, at very high strain rates. In this case, using electromagnetic loading, because this is a specimen tested by Lobinger at Rafael in Israel. But this could also, this experiment can also be performed using explosives. So the issue is that when we are subjecting to this high strain rate compression loading to the specimen, what we observe is that a number of shear bands appear in the inner diameter of the sample and they propagate, okay, following the maximum shear stress direction. So this experiment is very interesting because instead of having a single shear band like in the two previous cases, we have multiple shear bands appearing, basically because of the radial symmetry of the problem. And then the last example, it is dynamic voiding. So typically to study dynamic voiding, the most widely used experimental technique, it is plated pack experiments. So in plated pack experiments, basically what we have is the flyer and a target, okay? This is a typical Lagrange diagram. So this is time and this is the position. So this is the flyer, this is the target, and the flyer is impacting the target at very high strain rates. Typically the flyer is shot with a gas gun. So due to the impact, what we have is this compressive wave, okay? This is the impact interface. So we have the compressive wave, which is traveling through the specimen and is reflecting, is traveling through the flyer and is reflecting in the free surface of the flyer. And this is the compressive wave traveling through the target and is going to be reflected here at the free surface of the target. When reflected, this compressive wave transforms into a rarefaction wave, tensile wave, which is traveling here and is unloading the specimen. So the specimen gets unloaded, 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 and the same thing here. So once these two tensile waves, they meet here, the material is unloaded, and suddenly it is subjected to a very high tensile stress, very high hydrostatic stresses, and they lead to the formation of a spall fracture. So this is the typical signature of a spall fracture when we have voids that they have growth and coalesce inside the specimen that we are testing, just because of the interaction of waves inside the material. Here you can see some other examples of spall fracture that I took from a paper of Ameri et al. And Meyers 1983, where you can see here again the formation of a spall fracture, right? And these are different specimens of, if I remember well, tantalum that they were tested at different velocities. As we increase the velocity, we observe the increase in damage inside the material. Okay, so these are the typical experiments that you can perform to study these kind of problems. These are the problems I'm interested of. And here the issue is that we are trying to perform similar experiments, in this case for additive manufactured materials, and especially because we want to understand the effect of porosity on the formation of necks, and dynamic fracture, the formation of shear bands, and the growth of voids under dynamic loading leading to a spall fracture. So why we were using printed metals? Because again, it's easier to get funding if you say that you're going to test some fancy materials, and because they have this beautiful distribution of porosity. That probably for an engineer is not very nice, but for me was essential to have all this porosity inside my specimens so I can really understand the effect of porosity. So this is just an X-ray tomography, 3D reconstruction of a rendering of a 3D reconstruction of X-ray tomography that we perform at India Materials with my friend Fedesquet. So here you can see the distribution of different voids, which are nearly spherical inside the material. This is for a specimen made of aluminum, silicium, magnesium. This one here, and if I remember well, this is something like 2% of porosity, and with 2% of porosity, you already see all these voids inside the specimen. And we are performing the experiment, but we also need to do some modeling. So how are we going to perform the modeling? Well, normally, porous materials, they have been modeled using the Gurson approach, right? So this was developed in the 70s and then popularized by Needleman, Vedgar, and so on. And the basic idea is that if we have a porous material, right, we assume that this porous material has a microstructure which is something like this, right, with periodic microstructure. So we assume that the material has a periodic microstructure, and then basically we can use homogenization in order to transform this periodic porous microstructure into something like this, in which the porosity it is included in the flow potential as a single internal state variable. Okay, this has been very much used in the literature and really works very well and allows for solving many problems. So what we wanted to do here, it is not only to use this homogenization approach, but also include the actual porous microstructure. Because the reality is that if we use the homogenization approach, we don't account for the distribution of void sizes, we don't account for the spatial distribution of voids, and so on and so on and so on. And we thought that all these features are important. So we are performing calculations, importing into a finite element code directly the porous microstructure that we obtain from the X-ray tomographies. Okay? And we are comparing our results with the Gurson approach. And let's see if I have time to show some of these modeling results. Okay, so all this to say what? So the objective, as I said before, I repeated it already several times, it is to investigate the effect of actual porosity on the dynamic, localization, and ductile fracture with the application to printed metals. And we are performing impact experiments that I will show you now, and we are also running multiscale numerical simulations. We have done also a little bit of work on trying to develop analytical models, but this I will not show it here. Still, we have some analytical models also for analyzing the problems that I have shown you before. Okay, so the porosity distribution. So we have studied different materials, okay? So aluminum, stainless steel, titanium alloy, and Inconel, okay? And in all cases, what we have done is to take the samples and we obtain X-ray tomographies, and then we obtain the distribution of porosity. I'm just showing here the porosity distribution for different samples, okay? That they were also printed in different directions. So in total, we are analyzing all these porous microstructures. So here we are talking about aluminum printed in certain direction, let's call it direction Z, aluminum printed in direction or perpendicular to the plane XY. This is aluminum printed with different printing parameters along direction Z, and so on and so on and so on, okay? And this is stainless steel, titanium, Inconel, and so on. So we obtain the void volume fraction, that you can see that varies from 2%, the maximum void volume fraction that we obtain, up to something like 7, 10 to the minus 4%. So this means just only few voids, okay, per unit volume. And the voids were pretty large, so in some cases we saw, or we tracked voids that were larger than 100 micrometers in diameter. In fact, the mean size of the voids in most cases was above 10 micrometers, okay? So these are the porosity microstructures that we are analyzing, and then let me start with our research, the part of the test that we have been developing. What time is it? Okay. So first of all, I'll show you some results using some results that we obtained using the experimental setup developed in my lab for dynamic axial penetration of thin wall tubes. So very quickly, all the experiments, or most of the experiments that I will show you here, are either performed with a gas gun or with a Hopkinson bar. So in this case, we are using the single stage helium-driven gas gun that we have in my lab, okay? So this is the barrel. And the experiments are recorded with 2 high-speed cameras. So there is one here, and the other one is just right there. Basically, this experimental setup consists of shooting this or firing this conical nose projectile at velocities that range between 200 and 500 meters per second. Okay, so this is going to be far to penetrate axially a thin wall tube. The diameter of the thin wall tube is smaller than the diameter of the striker, and therefore when the striker penetrates the target, what happens is that the tube expands and fractures into multiple pieces. So we were testing different materials, those that I just showed you before. These are tomographies of the thin wall tubes that we tested. So again, this is just the cross-section of the thin wall tube. The projectile is going to, penetrate the target axially. The diameter of the projectile is larger than the diameter of the tube, and this is going to expand, okay? and we want to understand what is the effect of porosity. You can see here very clearly the porosity in the fragmentation of the specimens. And these are simply tomographies for different specimens printed with different printing qualities and so on. Okay, so we characterize the porosity before. Okay, so you can see here again a rendering of this portion of the tube. The tube is longer. This is just the end of the tube where the projectile impacted. So here you can see again the rendering of the distribution of porosity, the color coding. It is simply giving us an idea about the size of the pores, and this is the an histogram showing the distribution of void sizes for two different specimens that we tested. So assuming that the voids are spherical, which is a pretty good assumption, right? So we can see that the mean void size is around 15 to 20 micrometers, okay? And we still have some very large pores with diameter larger than 80 micrometers. And here I'll show you a video so you will see exactly how the experiment works. So this is the specimen, and this is the conical projectile coming. And again, this is the diameter of the specimen. So the diameter of the conical striker is larger, and the specimen is going to expand and fracture. So you can see how it's coming. You can see the cracks forming, right? And then it's leading to the final fragmentation of the specimen. So the idea here was to perform experiments at different velocities, to have a time resolve observation of the fragmentation process, to identify the number of cracks that were formed, and to identify the time for fracture, and if possible, the cracks speed. So we perform soft recovery of the fragment. Okay, so here you can see just snapshots of the test, okay, taken with the two cameras. And then here it's very easy for us to count the number of fragments. The fragments were recovered, were weight, size, and so on, to have the distribution of void sizes. And some of the fragments were also subjected to X-ray tomography analysis. And the idea was to obtain 3D reconstruction of the cracks. So this is just a fragment. This is the crack. And here you can see in orange, right, this reconstruction of the crack, in order to have an idea about the roughness and try to understand a little bit better the connection between the roughness and the toughness, and try to identify preferential loading, preferential paths for the crack to propagate, and try to identify the relationship with the porous microstructure of the material. So this is a pretty tedious work, and is still in process. Okay, this is something that we have already published last year in GMPS. Now we are writing a number of papers with the information that I'm showing you here. Something else that we also did, it was to compare the tomography before and after. And this is also very tedious. So basically, if you remember, we were taking X-ray tomographies of the specimens before, right? So we are recovering the fragments, and then we are trying to compare the tomography before and after, just to have an idea about the growth of the pores. So this is the tomography before. This is the tomography of one fragment. You can imagine that this is not easy because you have the whole 3D bunch of images, and you need to go image after image just to check if you can really compare. So, so this is before, this is after, and this is the superposition of both. Okay, the superposition is not perfect because the fragment deformed in loading and so on, but it still gave us some idea about the potential growth and shape change of some of the larger pores of the microstructure, and also gave us some information regarding the path of the cracks. Okay, so we did this for a bunch of fragments. And then, of course, we did the classical fragmentation analysis which is basically to take all the fragments. So this is the length of the fragment, the circumferential length of the fragment, and we took all the fragments and then we were plotting the histograms, trying to understand the effect of the impact velocity on the fragment size. So this is for a low impact velocity, and this is for higher impact velocity. So what happens is that as we increase the impact velocity, the distribution of fragment sizes narrows. This is very typical. What happens is, in this particular material, if we follow the ideas of Mott, of the theory of Mott of fragmentation in the 40s, it is that as we are increasing the loading velocity, the unloading waves emanating from early cracks, they don't have time to travel the specimen, and more cracks are formed and developed. Therefore, we have more cracks, more fragments of smaller size. So this is a trend that we obtained for all the experiments that we were performing. Okay. So that was the problem of the expansion of thin wall tubes. I will show you here the configuration that we developed to perform a radial expansion of rings, which in fact is based on the radial expansion of tubes. So again, you can see here our lab, right? So this is the gas gun, right? This is camera 1, camera 2, the lamp heads that we have here because we need to provide a lot of light in order to be able to record the samples, okay? And then what we did, it is to use the configuration for the expansion of tubes. And then we put the ring that we want to expand over the tube. So now what we have is that the conical projectile penetrates the tube, which is going to be made of a very ductile material. The tube expands, it pushes the ring, and then the ring fragments. Because the tube is like a pusher, way more ductile than the rings that we are testing. So here you can see again the projectile, and this is now the ring, and the ring is inserted over the ductile thin wall tube. So here you can see one video of the same experiment, the two cameras that we were using to record the test. So there we are, projectile is coming, impacting the thin wall tube, and this is the ring. You can see the formation of several fractures. And this is the same sample with the other camera. So we have a complete overview of the ring. So again, it's coming, pushing the tube, and fragmenting the sample. So in this experiment was really critical to be sure that the velocity, that the radial expansion, it is uniform, right? So what we were doing was to instrument the experiments using a PDB system. So basically the PDB allows us to record the radial velocity in different points of the outer circumference of the ring. So what you can see here, it is the radial expansion velocity of the ring as a function of time, measured with two PDB probes, which are like separated by 90 degrees angle, something like this. And the idea is that both of them must be or should be very similar, because otherwise my experiment is not radial expansion, it's something else. So luckily, we got a pretty good agreement, and you can see the recording of both probes, okay? And this is the increase in velocity, so the ring reaches something like 100 meters per second, and then we can also relate the different stages or the different points of the radial velocity curve with the corresponding fragmentation process. So we know exactly where the fragmentation occurs based on the PDB recording and the video recording that we have. And this is just to show you some images of the samples after testing. So again, we have here all the fragments, and we were able to measure the fragments and so on, and also perform some fractography analysis. So this is just the fracture surface of a given experiment, okay, of a given fragment. And you can see here, for instance, these large boys, Okay, so this is almost 90 micrometers in diameter. What is interesting, it is that between the voids, we have dimples. So this is kind of ductile fracture, despite we have these large voids. So certainly the voids are really playing a large role, but in the, let's say, matrix material between the voids, we have something like a relatively ductile fracture. And again, we were performing the fragmentation analysis, measuring the fragment sizes, and then plotting this distribution of fragment sizes. So this is for low velocity, and this is for higher velocity. And in the case of the expansion of thin wall tubes, as we increase the velocity, there are more fragments, and the fragment size gets smaller. So we were using, once again, mode analysis. So in this case, I am plotting not only the fragments obtained for a given velocity, but all the fragments obtained for all velocities that we were testing, and using mode analysis, which is basically giving you a length scale of the distance that the release waves emanating for fractures can propagate. We were able to obtain these beautiful plots where in red we have a fitting of the distribution, but in green it is just prediction by mode theory. So you can see that the prediction of mode theory, it is pretty nice and gives us a very nice idea about the distribution of fragment sizes. Okay, so the previous formula was the fitting of the Weibull PDF, and this is just the results obtained with the mode theory. So one interesting thing that we did was to compare our result for the ring expansion with the classical experiment developed by Rabi. So my student was 5 months rebuilding in Austin, rebuilding the setup of Rabi, and then we performed experiments, ring expansion experiments with the same material using the setup of Rabi to compare if our mechanical setup, because we only need a gas gun, provides results which are consistent with the electromagnetic setup of Rabi. Okay, so this is the Rabi's lab in Austin. So we performed the experiments, and what I'm showing here is a number of pictures of a given test. Okay, so basically in the electromagnetic loading, what we have is that we are inducing a current through the ring. Okay, and this creates these repulsive forces with the solenoid. Okay, and then the ring expands at very high velocity. So this is the specimen, this is the ring, this is T0, and then here you can see that the ring is expanding, and then here you can see these sparks. This is the signature of fracture, because as I said before, we have a current which is flowing through the flowing through the specimen. So when there is a fracture, you can see here the spark because of the current that was flowing through the sample. So again, there are here 2 fractures, okay, and the final fragmentation. So as we increase the velocity, so this is another experiment, again, the same material. Simply, we are here imposing a larger velocity, and we can see that there are more sparks, appearing because of there are more fractures in the material. And we also perform X-ray tomography analysis of the fragments. So this is just one of the fragments recovered from this experiment, and you can see here the fractured surface and some voids which are here a little bit more elongated near the fractured surface. This is the other end of the fragment, and again you can see here some voids that are more elongated, and we were obtaining the void volume fraction distribution along the circumferential direction, just trying to understand if where we have the fracture, the porosity has grown. So in these experiments of Ravi, we were able to record also the radial velocity. In this case, instead of using a PDB system, we just used the high-speed camera. So you could see here the evolution of the radial velocity of the ring, okay, for different specimens tested at different velocities. So this here in purple is the largest velocity tested, okay, and you can see that is if we decrease the velocity, of course, we decrease this maximum radial speed of the sample, okay? So again, we developed the same analysis, so we measured all the fragments, so lower velocity, higher velocity, we have more fragments which are smaller, and then again, mode analysis, blah, 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 and then let me go here, I'll show you the comparison. And then we compare the results with the setup of Ravi, which are called RE, so this is electromagnetic, and there's results that we obtain with our setup, okay, M, mechanical. So here, red, green, purple, so these are our experiments, are around here. This is for the evolution of the fracture density as a function of the strain rate. Fracture density, for all purposes, is the number of fractures per unit length. So with our setup, we can reach these strain rates, 10 to the 4 and above, and these are the experiments, okay, performed in Ravi's lab for strain rates of the order of between 5,000 and 10 to the 4. And you can see that even if we have a scatter, which is coming from the porous microstructure of the material, we obtain a very nice trend with this increasing evolution in the number of fractures as a function of the circumferential strain rate, combining both the experiments performed in Austin and the experiments that we performed in Madrid. Okay, let me, how much time I have? Okay, I have 5 minutes. So let me just remove this because I will show you something. Okay, here. So in addition to analyzing necks and fragmentation, as I mentioned, we are also analyzing formation of the shear bands. So something that I think is interesting, it is the series of experiments that we perform at the European Synchrotron Radiation Facility. So here we were running dynamic experiments that allow us to see in situ the evolution of the porous microstructure of the specimen. So using a Hopkinson bar, because there is a Hopkinson bar there on site, so we were testing this kind of sample. This I showed you before is the shear compression specimen of Rittel. So we are compressing this sample, and here we have this shear strain localization and the formation of a shear band and final shear fracture of the material. Okay. So this is the lab. So this is the ID19 because we performed this in ID19 where they have one Hopkinson bar. And then we can, this is the start movie. Yeah, this what you see here, it is the porous microstructure of the material. So this is the interior of the specimen, okay? So these are the pores, you see the pores. And this is just the recording about how the sample is tested in this direction. And you see the pores, for instance, they are closing, they are twisting, they are rotating, and eventually we have the formation here of a shear band and the final crack of the sample. So this is pretty nice because it's one of the first recordings that I know, at least, of the evolution of the porous microstructure of a porous ductile metallic material under high strain rate. So here the strain rate is around 10,000, something like this. And this is not working, but we were synchronizing the load displacement signal that we obtained from the Hopkinson bar with the video. So we know exactly when the pores close and when the fracture appears based on this recording and based on this video. Okay? So yeah, this is what I'm showing here. So again, loading versus displacement, and this is the evolution of the porous microstructure. And what we are doing now, but it's not over because this requires a lot of image processing, it is to track at least some of the pores and to have a reconstruction of the evolution of the pore. Okay? And comparing also the analysis before loading and the post-mortem analysis of the specimen. And then if you want, I will show you something about the spalling, and I can just finish with that. Okay, yeah, and then plate impact experiments. So in order to study dynamic boiling, we also are performing plate impact experiments in our lab. So again, we are using this single-stage gas gun. We have to modify a little bit the setup. So basically now we are shooting a thin plate of typically 2 millimeters, to impact, okay, to perform planar impact on the specimen. This is the specimen, which is a plate of typically 18 millimeters diameter and 4 millimeters thickness, okay? So we are recording the velocity in the rear surface of the specimen using our PDB system, and with the PDB system and the signal, we are able to obtain the spall strength of the material. And as in previous cases, we are performing tomography analysis before, tomography analysis after, okay? So these are just some samples tested at different impact velocities. So this is the incipient spall, you can see it here. So higher velocity, you know, the spalling is pretty obvious. And here, I think it was something like 700 meters per second. The spall is really huge. So we are able to compute for different printed metals the evolution of the Hugoniot elastic limit, for instance. So these are the beautiful signals that we obtain, right? So these are just the spectrograms. So you can see here the free surface velocity as a function of time. So the wave is reaching the free surface of the target. The velocity increases. This is the Hugoniot elastic limit. Then the plastic wave comes and reaches this Hugoniot plateau, right? And then this duration of the pulse, it is given or is determined by the thickness of the flyer. And then because the reflection in the free surface of the plastic wave, we have this decrease of the velocity. In this case, there is no spalling because the velocity goes to zero again. If we increase the impact velocity, you can see here the same profile of the signal, okay? But here, this is not very clear, but it's there. There is a pullback velocity. So instead of the velocity going to zero, okay, there is a reacceleration here of the rear surface velocity and goes up, which is the signature of a spall fracture. I increase the impact velocity, and again, the same thing. You can see here that this does not go to zero, like it was in this case. So this is the signature of a spall. Again, higher impact velocity spall, higher impact velocity spall. And again, with these signals, we can compute the spall strength for different materials and so on and so on. This is, in fact, what we are doing now with Mohammed, trying to understand the spall behavior of certain materials. And these are just the last slides that I'm going to show, because it's not only that we were performing spall experiments in our lab, we are also doing performing in situ spall experiments in the synchrotron. So we went to Grenoble. They have a gas gun there, very similar to ours. So one single stage gas gun driven by helium. So for us, it's pretty easy to operate it because it's very similar to ours. And then what was fantastic is that we had 3 Shimatsu cameras operating at the same time. So just for you to have an idea, the duration of the spall experiment in our lab is typically 2.5 microseconds. In the synchrotron, we have to scale down the specimen size. And when scaling down means that the process of wave reflection, takes less time. So it's even shorter. So I'll show you some signals. But in the synchrotron, when we are scaling down the specimen size, the whole experiment lasts around 1 microsecond. With the 3 cameras, we were able to obtain a frame every 170 nanoseconds. So we were able to see in situ a spall fracture, okay, and relate the spall fracture with the signal of the PDB system. I'll show you this now, okay? But just for you to have an idea about the numbers of the duration of the experiment and also the recording that we performed. So these are the signals, okay? So these are samples made of aluminum and titanium, both, We cannot go to higher densities because otherwise there is no transmission, but aluminum and titanium is more or less okay. And these are the signals. You can see that the plateau, it is much smaller than before because the specimens are smaller. And you can see the duration of the experiment, okay? So again, 1 microsecond. Here, there, there. And this is a tomography of the sample after testing. So you can really see here, the spot fracture. And now I'll show you the images. Let's see if you see. I'm finishing with this. So this is the flyer, okay? So this is the impactor. And this is the target here. What you can see here, this is because we are using a pyramidal support to hold the specimen, and this is just the printing layers. So this is not a specimen; it's just the what we are using to hold the specimen. So flyer is coming, and this is a sample. What you can see here, these white spots, these are the pores. Okay, we are still processing the images, but here you can see the pores. So this is before impact. This is empty. Okay, this is air. So projectile didn't reach the target yet. So it's coming. It's very close to impact. Okay, here is impacting. It is just right there. And now here you can start seeing. In the image that we have already processed, you can see it better. But you can start seeing that the pores, they disappear. Here the pores, they have already collapsed. Okay? These white spots that you can see here, there are many less spots, white spots here. It means that the pores are collapsing. And then here, most of the pores, they are already closed because of the compressive wave. Now the compressive wave has reflected, and here you see this white thing here, a little bit clearer. This is the spot fracture. Okay. So again, here with the presentation and everything, and the light is not perfect, but in the image after the processing of the images, you can see it very clearly. Here you have the spot fracture. And the cool thing is that we can relate the video recording with the signal. So we know exactly when a spot occurs, okay? So for instance, here, which is the incipient spot, that you can see it here a little bit clear in this section that corresponds to half the midsection of the specimen, it is here. In fact, this is very cool because most of the people, they think that the spot fracture occurs much later in time in comparison with the signal. However, the spot fracture occurs occurs already here at the very beginning of the Hugonio plateau. And if this is for, here with the light you don't see it so nicely. So, and this is as experiment performed with titanium. So this is why the transmission is worse. And here without light and so on and so on, you should see a white line here, okay, that is telling us that there is a spot fracture. And once again, we have the loading time because we have the PDB system, which is synchronized with the cameras. So we can relate the free surface velocity, okay, so the PDB signal, with the formation of a spot fracture. And I think I will stop here, as I was afraid that I was not going to have time for showing the multiscale modeling, but I think the experimental part was nice. So thank you.
Okay, thank you very much. So we have time for a few questions. Anybody from the audience? Yeah, go ahead, Lena.
So, did you image the local stress or local strain evolution?
In which depends on in which experiment. The local stress in the spot, yes, because we have the signal, and with that you can correlate the free surface velocity with the stress within the target. This is classic. In the in some of the experiments with the Hopkinson bar, yes, because we are using DIC analysis. So I have some slides there. So we are checking with DIC how is the buildup of plastic deformation and the buildup of strain rate, trying to correlate this with the evolution of the porosity. In experiments like the fragmentation or like the ring fragmentation or the tube fragmentation, it is almost impossible because the thing is flying. But at least we can track the radial velocity with the PDB system. this is what we can have. And this allows us to obtain the strain rate, so it's not bad. I mean, it's not easy. The instrumentation of these experiments sometimes is not really easy. But yeah, we have some quantitative data.
Very useful for modeler.
Yeah, we have, I mean, we are using modeling, I mean, we are performing modeling, and we are validating our modeling with the final microstructure and with the, in the case of fragmentation, with the radial velocity, because with this we have it. In the case of shear, with the strain fields at the surface. Okay, so yeah, we have quantitative data that we are using for the modeling, but again, we did some modeling. We published a number of papers with modeling, but I'm sorry, I don't have time.
Okay, yeah, go ahead.
So, was there any possibility to measure the temperature inside the shear bands or anywhere? A lot of papers show adiabatic heating and liquefaction also happening.
Yeah. Yeah, it is possible, but I don't have the equipment for that. But a priori, it is possible. You can use infrared detectors. Danny Riddle at the Technion is using infrared detectors to do something like this. So yeah, it is possible.
And another question is, from your experimentation, could you suggest the type of properties a person should look for in a material so that you can avoid shear localization and make them resistant to these types?
I think we can get some trends. Yes, for sure, because we are getting a lot of data. We are comparing a lot of experiments. I'm not showing you here some comparison, but we also perform some experiments with different. It's not all, this, my excuse here was printed because of the funding, but we have been doing this for many other different materials. So yeah, a priori you can get comparisons, and when you get comparisons, you are getting some trends about what is important of this material to get less fragments, more ductility, less ductility. It is possible, yeah. One of the nice things of these experimental setups is that now that we really have a little bit mastered the technique, we can really perform a lot of experiments. So normally I'm going to the lab for 1 week, and then we came out with, I don't know, 50 fragmentation experiments, which is quite a lot.
So like high yield strength, work hardenability.
Yeah, for instance. Yeah. And also the fracture toughness and things like this. So yeah, I mean, sure.
Okay, any more questions? Just a quick question. So you looked at AM specimens. So the basic, very basic question, which one, I mean, if you have an AM specimen, you have a classically manufactured specimen, which one would be more impact resistant for the same material?
Okay, I think, yeah, this is a very good question. I think this depends very much on the loading path. Because, for instance, as far as we know, for this ring expansion fragmentation or the tube fragmentation, the porosity is not good, and then under tension, this is not working properly. For the small experiments, this is a little bit more tricky because when you have porosity, the porosity is dissipating a lot of energy of the compressive wave. So it means, in fact, having some porosity for a small fracture may not be bad. But for the ring fragmentation, which is basically uniaxial tension, and for the tube fragmentation, which is somewhere between uniaxial tension and plane strain tension, then pores are not really very good.
So you're saying like with AM, we might have more porosity than classical manufacturing?
Yeah, probably yes. But again, our research was most focused on the fundamentals. I think now we are ready to answer some more practical questions because we can really perform a lot of experiments and perform a lot of analysis.
Okay. Thank you, everybody.
Thank you.
And we'll see you at the next seminar then. Yeah.
You also see the wooden mutation, Julian stuff grows.
Yeah. Okay. Yeah. Yeah. This is why we are checking the tomography before and after.
Yes.
Identifying the new created bodies.
How to differentiate?
Yeah, with a lot of images. So this is why many of these things are not published because basically what we are doing again is comparing the former tomography, I mean the tomography before and the tomography. but there is a limitation for the new one, which is the resolution of the tomograph. So now, yeah, that's the problem. If they are very small, then forget it. So, but some of them they have grown a lot, so we can track it. But that's it. Because the resolution we are having, it is something like 1.5 micrometers. Less than this, we don't see. However, we are also doing some fractography analysis.
But you know, if you come to that, something pop up, you know that's the nuclear.
Yeah, exactly. So with the comparison, if there is something that was not there before, and we are also doing some fractography analysis, and then with the microscopic EPT.
Yeah, if you consider nucleation, I'm worrying that will give us complexity when you're correlating porosity size or distribution with strength. Because we really correlate the initial porosity distribution size with the strength.
Yeah.
Or something is coming out during
Yeah, it's very good.
Yeah.
This is why to give, like very clear correlations with is very good. But we try.
I didn't see you put a correlation porosity strength. You didn't put it there.
No.
Yeah.
No, I understand that these things are very, catchy, but I don't have it.
Okay.
This will be too easy.
Another follow-up question is I think you answered the question as well. Additive manufacturing method would be very good at it. With porosity, would be really good at it. With that's
It's not good. Also, because in compressive loading, you have the wave and it's dissipating air. This is very cool because you are having the wave, and instead of having a very thin front, the front is getting submerged. So that dissipates energy, decreases the intensity of the shock, and then the fall with porosity, you can kind of reduce the amount of support fracture. But for tension, what we know is that it's not really. On the other hand, the reality is that the mechanical properties are closing.
That one is opening.
Yeah, but in small they close and then they reopen. The issue is that in the process of closing, they dissipate.
Yes, that's right.
And this part is very important. What I was going to say, the issue that is also that the mechanical properties of the additive manufacture and the mechanical properties of the traditional manufacture are never the same. In fact, I was testing titanium printed and titanium produced in a usual manner, and the yield strength of titanium printed was high. So, this also creates a little bit, complicates everything in order to say what is.
Okay.
Thank you. Thank you for inviting me.
We have to discuss a few other issues.
Yeah, sure.
How's everything? How's everything going? I can't believe that the time was here, that there's a candidate.
Okay, I'll see you there.
Very nice talking to you.
Thank you.
I'll see you at DMS.
Yeah, perfect.
Okay.
Take care. Thank you.
Hola, mucho gusto. Mi nombre es Yasmin. Felicitaciones por su presentación.
Oh, gracias.
I wanted to introduce you. This is Yasmin Gonzalez.
Okay,
She's visiting us from Chile, University of Chile,
nice.
and she's mostly involved in earthquake analysis.
Oh, wow.
So her advisor, I got to know him at the meeting in Chile, very nice guy, and he said,
Yeah.
we need to send you this very nice person to just spend some time in North Carolina.
Nice.
She's doing very good work on earthquake analysis. So she's kind of at a different frequency than the impact, more on intermediate frequencies than this high impact, but there's some ideas there that could be very useful for her.
Nice. Very nice. So you enjoying your time here?
Yeah, Raleigh is very beautiful. Estoy trabajando con, con la falla del conector, entonces tu presentación es muy importante igual. Y es una parte también. También soy parte del Instituto de Ingenieros de Chile. Y estoy buscando un profesor que hable español y esté bien metido en la ingeniería como tú. No sé si te gustaría ser parte.
Seguro. ¿Qué es lo que necesitas?
Es una presentación solamente virtual.
Okay.
Es para divulgación científica, no, más que nada.
Perfecto, envíame un correo y lo que necesitas.
Ok,
¿Seguro?
muchas gracias.
¿Tienes mi correo por ahí o quieres que te lo dé?
Sí.
How's it going? Yeah, maybe I can call you later.
JAR,
JR,
MAR,
10 minutes or so.
TI,
Yeah, my schedule,
arroba,
I saw your email, my
arroba,
schedule is
ING,
right now to go
¿ok?
punto,
Yeah,
UC3M,
different visitors, I know
UC
the pressures you're under, but.
M, punto, ES.
Gone completely.
A ver.
Okay, thanks.
Todas con minúsculas, porque no sé si funciona, pero vamos, sí.
Ya,
¿Vale?
gracias.
Yeah, I'll swing by. Yeah, good luck with that search.
Hey, Jose.
Hi.
How you doing? I'm Tim.
Hi.
Nice to meet you.
Oh, nice to meet you.
That was
Yeah.
a really great talk.
Thank you.
Thank you.
Thank you. How are you?
Nice. I got you next. I'll take you to the lab tour.
Oh,
here,
yeah.
And then I think I'll take you to lunch. I'm not sure. I was going to check with Mohammed here and see what his plan was.
Okay.
All right.
Nice.
So whenever this is I don't. Did you mean Haji?
Yeah,
already?
yeah,
Okay. Okay. So Haji's the one that did all the work here.
Oh, the specimen, yeah.
So you'll give them the tour of the lab?
Yeah. Do you want me to take him right to the lunch right
yeah,
afterwards and
yeah.
meet up
We'll
with
meet
you?
you at the lunch.
Okay. Perfect.
And why don't you join us for the lunch?
Oh, me?
Yeah.
Yeah, sure, no
Alright,
problem.
Yeah, join us for the
Perfect.
lunch, and you two can also join us for the lunch.
Yeah, that's great.
And that way, in case you're doing something for dinner or something, don't worry about the dinner. Maybe lunch will be more.
Yeah, of course.
And then we're also meeting with them on that.
At 3:15.
Yeah. Okay.
And that's at your office?
Yeah, let's meet in my office. I think we have enough chairs. Yeah. Okay.
Not far.